Check. 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 Okay, you just have one more minute to pick up papers. This is the most organized homework delivery and drop-off that I've ever seen in my life. It's usually much, much worse. They're being dropped off in alphabetical order. They're being returned in alphabetical order. I'm shocked. Okay, so let's begin now. Why does everybody take their seats? And if you're still working on this, either turning in or dropping off, turning in or picking up, do so at the end of class, okay? Did anybody drop off their papers on the stage? No, they didn't, okay. If you did, they're to be dropped off on this table here. I'll drag it out so everybody can see it. Okay, but again, after class. After class. Yeah, thank you. Okay, so how are we doing? PA4, you guys asked that it be extended. I extended it 2 days to Sunday, February 26, 10 p.m. Huh? So I hear the plaintive wail of somebody needing more. How many people think they need more time? Okay. Will 2 days do it? It'll give you the week. No. All right, what I'm going to do is, because I'm going to at least start with DFS today. PA5 is on DFS. I'm going to post PA5 probably today or this weekend. I will extend it 2 more days. That makes it Tuesday, 10 p.m. Remember, there's always a 12-hour grace period. And we'll discuss it again on Monday, but I think we're reaching the end on PA4. So let's try to get something done on PA4. Let me just ask, so PA4, 2 days. Two more days. How are we doing on PA4? PA4 is breadth first search. We only really just finished it Wednesday. I have a few more words to say about runtime and things like that. Oh yes, I haven't actually talked about the get path algorithm or the print path algorithm. I'll talk about that today. So I think I probably owe you these other 2 days. But where are we? Does everybody have their graph ADT mostly built, with the exception possibly of BFS and GetPath? How many people are in that situation? Okay, that looks like about half. I wish it was more. But hopefully this weekend everybody will have that graph ADT up and running, tested. I honestly think that the top-level client, what's it called again? Find Path. that is pretty easy to write. You read the input file, you call add edge a bunch of times, and then you run BFS, and then you just do a bunch of queries that correspond to the second part of the input, queries of the graph struct, or of the graph ADT itself. Does that make sense? Like you find the D values and the P values, and you call this function find or get path in order to do them. So, okay, so I won't discuss that. Or are there any questions? Maybe I should open it up. Are there any questions on PA4? Midterm 2, yes. I will post review problems. I have some review problems. I'll post them tonight. It is 1 week from today. And what's on it? Everything through end of business Wednesday, right? That's what's fair game for the midterm. Everything up until the last lecture before the midterm. I will post solutions. You should be, studying homework solutions. Is it cumulative? Well, only insofar as it has to be. I'm not going to go out of my way to test you on Stirling's formula again, but gee, that's knowledge, that's background knowledge now for everything that we do in the future. What else? Anything on PA4? So nothing on, everybody knows what they're doing on PA4. They're not completely lost. Remember, you do have to, you do need to make sure that there aren't memory leaks. So you know how to, I think I said somewhere how to run Valgrind. Make sure you test it under Valgrind. But Valgrind does more than test for memory leaks. It finds memory errors, illegal reads and writes, and you should pay close attention to those. You'll lose points for any kind of memory error, like an illegal read where you're trying to read past the end of an array or read at some area of memory that is not at this point in time allocated, or worse yet, to write to such an area of heap memory. All those will be found by Valgrind. They could indicate deeper logical errors in your list. That's the real reason that you want to do this, because if you're doing that, there's probably some logical error that you were unaware of in your list or in your graph ADTs. Most likely in your list if you're getting memory errors. Question over here? When will it be posted? I will post it as soon as I can, like tonight. Okay, so people who are done with PA4 can get working on it. Anything else? Go ahead. Yes. So I recommend that you create some constant macros. You know how to do that. Pound define, name of macro, value. Those are literal text substitutions. So anything with a pound in front of it is a preprocessor directive. And the first pass of the compiler is to just go through your code and do these literal text substitutions. That includes the pound includes. Pound includes just literally shoves some code into the beginning of your code. The pound defines go through and they replace every instance of nil, say, by whatever integer you decide to make it. All right, so what are the constant macros? I think it's useful to have a constant macro for nil. So what does that need to be? Any integer that cannot be the label, the legitimate label of a vertex. Vertex labels are always greater than or equal to 1. They range from 1 to the number of vertices in the graph, n, whatever that is. So anything other than those integers is a viable candidate to define nil to be. Don't make it null. Null already has a special meaning in the C language. It's the undefined pointer value. So if you were to try to assign null, I saw somebody doing this yesterday, try to assign null to an int variable, you will get a warning at least that says something like, assigning pointer to int without a cast or something like that. Don't do that, right? And if you see a warning, don't ignore warnings. Warnings are important. So you need an int value. 0 is a good one. 0 is a pretty reasonable choice for nil. What about inf? At no point do we compare inf to another integer as to its size. So it doesn't need to be a gigantic integer. Like some people think, well, maybe I'll make this the maximum possible int value, right? And you can figure out what that is. Of course, that's platform dependent. It depends on how many bytes go into an int, doesn't it? But since we're never comparing as to size, we're only comparing to see if, actually we never compare infinity to anything, right? It's just a label that means unreachable. That's all it is. Any negative number is a valid value for infinity. Now, does your value for inf need to match somebody else's value for inf? No, they don't, because if I were to hook up your list with their graph, I'd be using their graph.h. And their graph.h would have their constant macro for inf. So that's why that particular choice should be considered inside the black box, right? That's not part of the interface. Any other questions? Go ahead. There's the same 2 or 3 people up in front are asking the questions. I'll look back there the next time. Go ahead. What number? Edge number. Size. Size. Okay, so is this the question about add edge versus add arc? And what does that do to size? Okay, I did answer this last time. Add arc adds 1 to size. Add edge adds 1 to size. That's the answer to the question. So, what's wrong with that? Add arc adds a directed edge. Add edge adds an undirected edge. It is not contemplated that this model of a graph, that this computer model of a graph, is going to be used to represent a mixed structure that contains both directed and undirected edges. Such things do exist, and some people work with them, but that's not what this graph ADT is meant to try to work with. So you're only building a directed graph or an undirected graph, not some kind of mixture of the two. So there's no conflict because it never happens. Go ahead. I don't understand the question. Ask it again. Does the code, does a graph know if it's directed or undirected? Right. These are interesting possible expansions of this graph ADT. Add a field called type, and the type would be a string, and the string would be either directed, undirected, or maybe mixed. Maybe there are 3 types of graph. None of that is required. Since it's under the hood, and since it's not part of the interface, then you can add it if you want. Okay? Does that make sense? I mean, after all, maybe a graph should know its own type. Question, way back there.
So, in that case, for our add arc method, do we not have to account for if there's a directed arc going in the other direction?
That is correct. Okay. That is correct. If at some point I call add arc xy, and then edge goes up by 1, or size goes up by 1, then at some later point I called add arc yx, size goes up again. So that counts as 2 edges, 2 directed edges. Even though the same arrangement of adjacency list exists as 1 edge if this were a undirected graph. Make sense? Well, we don't mix those structures, so it doesn't matter. I answered all this last time, but to a guy who was sitting over there. I forget who it was. Anything else? All right, let's proceed because we've got a lot of room, a lot of stuff to cover. Now, what did we do last time? We talked about BFS. We ran it on 3 examples. In each case, we run it on directed, undirected. It runs the same in either case. Basically, what it's doing is filling in this table. Given the adjacency list, that's this column, it fills in the other columns. Actually, this is the only case where I filled in all 3 columns. So the leftmost column is the input. The output of the algorithm is to fill in the rest of this table. Basically, all that the algorithm does. But of course, we can draw a picture. If I ask you to do this on an exam, I'm going to ask you to give me the order in which vertices entered the queue. Well, a list of numbers crossed out is a perfectly good way to answer that part of the question. So this is basically what I would expect to see on a midterm question, right? Now, what about this BFS tree? The BFS tree that is encoded by the parent fields is called the predecessor subgraph. That predecessor subgraph is defined abstractly by these 2 sets. VP, that's the set of all vertices in V, such that parent of X is not nil. Everybody who has a parent, together with one vertex who doesn't have a parent, that is S. In other words, all the vertices that were discovered. If you look at the code, that means all the vertices that are not white anymore, right? Because the minute we color something gray, we set its parent to be something other than nil. So these are the vertices that got discovered. That's what it is. Together with S. S never gets a parent, but it was discovered. And then EP. So P is for parent or predecessor. So this is the set of edges of the form parent X to X in E, such that parent X is not nil. In other words, X is one of the vertices in VP other than S, somebody that has a parent. So this pair is understood to be an ordered pair if the G is directed. It's understood to be an unordered pair if G is undirected. And that's the predecessor subgraph. There's the vertex set and the edge set. GP is VP EP. It is necessarily a tree because on the one hand it's connected. I could, because there's a line of parents. I could prove this, but there's a line of parents going all the way to the source in every case, so it's connected. And also, if you just count, the number of edges is one less than the number of vertices. Question?
When we're drawing the graph, does it have to be like in the nose where it starts at the top and works its way down? It can't be both towards the shape of the graph and then just doing an extra edges.
I'm not sure if I understand the question. When you're drawing what? The graph or the tree?
The tree.
When you're drawing the tree, yeah.
Format, or can it be like how the book has it, where it just shows like an overlay of
I see. So the question he's asking is, do I need to draw the tree, the BFS tree, as a separate graph, or can I just darken the edges that belong to the tree within the graph itself? Is that what your question is? It depends on the wording of the question, but I can tell you that on an exam, I'll word the question in such a way that I want to see it as a separate graph, the way I've done here. Okay. Okay, so that's the predecessor subgraph. Once you have that predecessor subgraph, so do you see why this is a tree? Going back to the treeness theorem, it's connected because every vertex other than the source has a parent, and they have a parent, and they have a parent, and they have a parent going back to the source. So everything is connected to the source. So therefore it's a connected graph. But you can count the number of edges because you can count the number of times that is true, and it's one less than the number, it's exactly the number of times that is true. And that's one less, the one being S, than the number of vertices. So therefore, by the treeness theorem, or one of the lemmas preceding the treeness theorem, this is a tree. Okay. And I think I should do this thing, right? Document camera 1. How's that? Good enough? Is it in focus? Move it. How about I do this? How's that? Okay, but is it still in focus? Okay. All right, so I think I gave you these exercises before. Let me give them again verbally. Go through all of these examples, these 3 examples that I did, and pick different sources. Rerun BFS. Also, rearrange the vertices in the adjacency lists. In other words, process the for loop inside the while loop in different orders, right? Process this adjacency list in a different order than was done. And see the different results you get when you do that. That's an exercise. I forget now what oh yeah. So how can we extract shortest paths? Once we have the tree, you can see what the shortest paths are. For instance, a shortest path from 3 to 5 is 3, 2, 5. A shortest path from 3 to 10 is 3, 6, 8, 9, 10. So all the shortest paths from 3 to everywhere reachable from 3, in this example, oh, I'm looking at the, darn it. Okay. Now I got to wait a half hour for this thing to come up. There we go. So 3 was the root. This is the last example that I did. 3 to 5, 3, 2, 5, that's the shortest 3, 5 path. 3 to 7, 3, 6, 8, 7. Let's look in the graph. 3, 6, 8, 7. It looks like the only shortest 3, 7 path. Well, I'm sure there are some, yeah. For instance, 3 to 9, what's the shortest path? 3 to 9 is 3, 6, 8, 9. 3, 6, 8, 9. But 3, 2, no, that doesn't do it, does it? It looks like shortest paths seem to be unique in this graph. So the question now is, given nothing but these parent fields attached to each vertex, how do you actually find these shortest paths? The book has this algorithm called print path. Print path input is G, an adjacency list representation, the source vertex S, and the destination X. Precondition is that BFS has been run with source S. You're going to be able to test that precondition because I'm asking you to add a field to your graph structure so that a graph knows who its most recent source was. Which of its vertices was the most recent source to DFS? So you'll be able to test this condition. Also, in a way, you don't really have to test this condition. So why even have that as an input if that's the only source you're going to use, namely the most recent source to BFS? So the version I'm having you write for this project is called getPath, and it doesn't have the source as an argument. It's just from the most recent source. And if there has been no source, if the graph was built and BFS was never run, that's a violation of a precondition. But you test that precondition by looking at the source field in your graph struct. Okay, what does this do? 1, if X happens to be the source, I'm just trying to get from source to source, so print S. This is pseudocode, so don't worry about what print actually does. What's the format? What's it going to? Standard out. There is no standard out. This is pseudocode. Else, if parent X is nil, I guess that should be double equals, right? If parent X is nil for print no path from S to X. What am I doing here? Exists. You see what I'm doing? The plus signs are supposed to be concatenation. In other words, no path from S to X exists if parent X is nil. That means we never discovered X. So this is not an error condition, but this is just what should be printed by this print path. 5, else, if neither of those are true, then we have a recursive call. First of all, 6, print path from in G from S to parent X. 7, then print X. Do you see how this works? Do you see how it's important that I tested these two conditions in this order? Because if I tested this first, I wouldn't ever be able to print S to S. Right? I wouldn't be able to print the trivial path because the source has no parent. First, check that whether we're on the source. That's a trivial base case. And then check if there even is a path from S to X. And now, in the final else, I know there's a path from S to X. First print the path from S to predecessor of X, and then print X. So this prints a sequence, and this terminates the sequence with the last step. This is the recursive call. Now this is how I want you to write getPath. Don't write it iteratively. Some people say, I don't know how to do this by recursion because I hate recursion, and I'm uncomfortable with it. So therefore, I'm going to call BFS on X as the source and then follow the pointers from X to S, or from S to X, right? Find the descendant S and then follow the pointers from S to X. Wrong, I don't want to see that. Furthermore, the version I'm asking you to write doesn't print anything. Instead of printing, what it does is appends to a list. So one of the inputs to the algorithm is also a list reference. So it just appends to a list. In this project, you're going to start with an empty list and start appending vertices. And then when you want to print out a list, just call print list, right? When you want to actually print it out, you just call print list. Notice I've left open the possibility that you're appending to an initially non-empty list. Now, that would make sense. If you think about it, you can do this sort of thing on Google Maps and on MapQuest and things like that. You can plan a trip from here to the mall and then add a destination, right? So I want a shortest path from here to point A, and then a shortest path from A to B, and then a shortest path from B to C, and then a shortest path from C back to home. So the whole thing isn't a shortest path, but it's a concatenation of shortest paths. So this get path algorithm could be used in that kind of a setting. It's not what's happening in this project, but that was the thinking behind it. Remember, what this is sort of, I think, a first draft of a very general graph ADT that can be used for answering all kinds of questions in a big, complicated graph. It could be, part of an engine in something like Google Maps, something like that. Okay. Any questions on print path? Everybody understands the recursion, I hope. The only thing left on BFS is the runtime. Well, first of all, if you look at the code, I tell you what, let's go back to that. And I see that I forgot to. You're still seeing the. Keep forgetting to switch this other. Let's look at the code while I do this. All right, lines 1 through 9 are all initialization. The cost of initialization is theta n, where n is the number of vertices, m will stand for the number of edges in the graph. And that's because we've got to initialize every single vertex. And calling the constructor of a queue, that's constant cost. Okay? Now let's look at the while loop. The queue operations. What's the total cost of all the queue operations? Well, look, every vertex enters the queue at most once, because only white vertices, let's see, the source is added to the queue, and after that, only white vertices get entered into the queue. And the very first thing we do when we pull a vertex off the queue is color it gray. I'm sorry. Let's see. After we pull it off the queue, we color it black. But as soon as we push it into the queue, it's colored gray. So therefore, vertices go through the queue at most once. Queue operations are therefore big O n. That's the cost of all the calls to NQ and DQ put together. It could be less than n, because not every vertex is necessarily discovered, so not every vertex goes through the queue. What about scanning adjacency lists? That's the cost of all iterations of this inner for loop. Right? The total number of times that body is executed. That's what I'm getting at. That's what I mean by the cost of scanning adjacency lists. Well, since every vertex goes through the adjacency list at most once, every adjacency list is scanned at most once. It is theta m. Notice that the total length of all the lists is equal to 2m in the undirected case, and it's equal to m in the directed case. And in either case, that's theta m. This was the handshake lemma, you remember? And I didn't get to it in the handout, but there is an analog of the handshake lemma for undirected graphs. So remember what the handshake lemma said? The sum of all the degrees. Well, that's actually the sum of the lengths of all the adjacency lists. The sum of all the degrees is nothing but twice the number of edges in an undirected graph, because each edge contributes 2 to that sum. In the directed case, each edge, there are 2 degrees. There's the in degree and the out degree. So the analog to the handshake lemma is that the sum of the in degrees equals the sum of the out degrees equals the number of edges. And that's because every directed edge adds 1 to the sum of the in degrees and adds 1 to the sum of the out degrees. Okay, so that's the cost of scanning adjacency lists. So the total runtime is theta n plus m, the sum of all these costs, theta n plus m. Now let's just think about that for a minute. Too bad it's not simpler like theta n or theta m. But actually, look at the underlying data structure. It's an array of length n, and what's in that array? A bunch of lists whose total length is m. So n plus m is a good measure of the size of the input, right? Because the number of bytes needed to store the adjacency list representation is some constant multiple of this quantity, n plus m, right? Does that make sense? So this is a linear algorithm. It's linear in the size of the adjacency list representation. In other words, this is a very efficient algorithm. If you just thought about it at first, you might think, wow, finding all shortest path or all distances to all vertices in the graph, that sounds like a daunting problem. Who would have believed that there's such an efficient algorithm to solve it? This is highly efficient. And even on very large graphs, you can run this algorithm, and it runs almost instantaneously, right, an imperceptible amount of time. By the way, is this still up? You can create gigantic graphs if you want to. Examples, PA4, random input files. So you can create a random, I won't try to explain that. That's some Java, some Python code. But you can create a random input graph with 1 million vertices if you want. If you don't mind using a bunch of space. and then run this on it and try to find distances. Question over here? Go ahead. About what algorithm? Yes? That's right. As a matter of fact, I think I mentioned this last time. You could get rid of the colors. So why are they there? They're there, and the same is true in DFS. You'll see that there are 3 colors in DFS, white, gray, and black. The real reason they're there in the book's presentation of BFS and DFS is so that they can reason about, they use the colors to reason about the running of the algorithm, and in particular, prove the correctness of the algorithm. So there is a proof of correctness of this algorithm, and I urge you to read it. I'm not going to cover it in class in the interest of time. And the colors are used there. We could get by without these colors. Question?
So would a more precise runtime for DFS be data 2n plus 2n?
No, because remember, constant multiples don't have no effect.
Just be more precise.
Yeah, but then take it out of the theta. If you want to be that precise, don't use asymptotic notation, because asymptotic notation is, by design, imprecise. See what I'm saying? Asymptotic notation isn't precise about coefficients. It's supposed to be imprecise about things like that. Okay. Well, all right, so let me make sure that I switch this back. All right, so we started BFS by posing a problem, SSSP, the single source shortest paths problem. And the solution to it is BFS. What else can you do with BFS? Actually, you can discover if a graph is connected or not. How do you do that? Pick a source, any source, run BFS on that source, and then look at the colors that have been filled in. If they're all black, then it's connected. If there's any white vertices left, it's disconnected. You can actually modify this with several runs of BFS in order to determine the number of connected components. So run BFS. If everything is black, then fine, it's got one connected component. If there's anything white, pick a white vertex and run BFS on that. But don't change the black vertices. Leave the black vertices intact. So I guess you have to rewrite BFS so that it doesn't initialize the colors. And then, what's going to be discovered is everything reachable from that second source. If anything white is left, then run BFS again. So the number of times you run BFS until everything is black, that's the number of connected components. And for that matter, the set of BFS trees you get for all those individual runs of BFS, those are the vertices in the connected components of the graph. So you can actually find the connected components. All right, so this is 22.3, depth first search. DFS. What problem does it solve? Well, I'm not going to tell you what problem it solves. The book does this too, you're right. I'm not doing this on my own. We're going to take a completely different approach to introducing DFS. I'm just going to show you the DFS algorithm, calculate its runtime, start learning things about it, run it on a few examples. Before we even know what it does, what problem does it even solve? So that's kind of an outstanding question. The reason we do that is it solves many problems. There are many structural details of an undirected graph and a directed graph that can be found by running depth first search. Sometimes you have to run depth first search a number of times, a few times in order to get it. Okay, and it's going to be what you implement for PA5. So first, vertex attributes. They are, as before, color, color of X is going to be white, gray, or black. And they mean basically the same thing. White is undiscovered. Gray is discovered, but we haven't finished working with it yet. Black is we're finished. This isn't finding shortest paths. It does find, and it does create some trees, but they're not shortest paths trees. P of U, or P of X. This is, again, the parent or predecessor. Of X. So we are going to be creating a subgraph. That subgraph is not a tree necessarily, it's a forest. In general, it's a forest. It could be a tree, but... And D of X and F of X. That's not a distance. These are discover and finish times. So timestamps. So we have a clock. We have a variable time that ranges from 0 upon initialization up to twice the number of vertices. Again, n throughout most of this discussion is going to stand for the number of vertices, m the number of edges. Why 2n? Because every vertex will be discovered. Even if it's, and by the way, there is no source. Some people are always a little confused about DFS. BFS had a source vertex as input. DFS has no source. So, and in BFS, not necessarily every vertex is discovered, but in DFS, every vertex in the graph is discovered, whether it's connected or not. So since every vertex is discovered and each one has 2 timestamps, and they're all different numbers, time is going to reach 2n. Okay, DFS is recursive. And it calls a well, first of all, the DFS algorithm is split into two functions. DFS calls a recursive function called visit. And visit is where the recursion is. This is what's recursive. So the DFS function calls the visit function. Visit is recursive. The whole thing together is the DFS algorithm. Okay. Here's the DFS algorithm. I can pull that up a little bit. All right. So what happens? DFS. Notice there's no source as input. It's just the graph in adjacency list representation. And just like BFS, it runs equally well on directed and undirected graphs. So for all vertices in the graph, color that vertex white, set its parent to nil. So all vertices are initialized the same. We don't bother to initialize the timestamps, discover and finish times. Okay, I guess we could. We set time to 0 in DFS. Now this time variable is local to the DFS function, but it is global over all recursive calls to visit. So you'll see that time is mentioned within visit. So this is not an input to visit. This is, as far as visit is concerned, this is a global variable that it is manipulating. And the global variable belongs to the sort of parent process, which is DFS. All right, so we enter a loop, 5 through 7, and I usually refer to this as the main loop of DFS. For all vertices in the graph, if the color of X is white, then visit that vertex. That's all it is. So if on the surface, it looks like, why even ask that question? You just colored everything white. How could that color be anything but white? And the answer is, the call to visit is going to change the colors of many vertices in the graph, not just the color of X, but the color of other vertices reachable from X. So by the time this call to visit returns, the next iteration of this for loop, it could be that none of the vertices are white anymore at that point. Right? So that's why this needs to be tested. True, though, on the very first iteration, since no call to visit has occurred yet, this will necessarily be true on the first iteration of this for loop. Okay, so now let's see what happens in visit. Visit is where the real work is happening. It's a little hard to understand just because of the recursion. Okay, so what do you do when you visit a vertex X? The first thing you do is color it gray. That's considered a discover event, coloring it gray. And then as soon as that discover event has occurred, what we do is give it a timestamp, a discovery timestamp. So first increment time, and then assign that incremented time to the discovery time of X. Put that timestamp on X. Notice that I used the prefix version of the, what do we call this? The auto increment operator. By now you know what this means in C and C++ and Java. First increment, then the value of this expression in parentheses is the value after the increment. So when time starts at 0, the first increment that takes place is from 0 to 1. And so 1 is the first timestamp. 0 is not a timestamp that ever occurs. It's just the initial value of time. Then we enter a for loop. What does the for loop do? The for loop processes the adjacency list of X. It goes down the adjacency list. And looking at each element on the adjacency list, one by one, test and see if that vertex on the adjacency list, so this is a vertex adjacent to X, see if it is discovered or not. If it's white, that means undiscovered. If it's undiscovered, set its parent to be where it's discovered from, namely X, and then visit Y. So here's the recursive call, and this is where the algorithm gets confusing. At this point, you have another call to visit, and you go one level deeper into the recursion. Okay, one way or another, though, all those calls to visit return, and you come back, and you've finished processing this adjacency list of X. Once that is done, we set the color of X to black. So we color X black only when it has no undiscovered neighbors, or only when this for loop is done. Okay. That's considered a finishing event. So what do? Increment time, and then set the finish time of X to that new time. Now you might say, well, wait a minute, these are one apart, aren't they? No, they're not one apart, because in between the two timestamps are some calls to visit. And these calls to visit themselves could increment time a few times. So do you see that the recursion is an important part here? Just like in BFS, we have a predecessor subgraph. The vertex set is the whole set, so all vertices will be discovered. The edge set is defined exactly as before. It's all vertices that have a parent. And just as before, this pair is an ordered pair if it's a directed graph, an unordered pair if it's an undirected graph. All right, so that is the DFS algorithm. Let's run the DFS algorithm on some examples. Maybe just by doing that, we'll get some sense of what it does. 4, 5, 6. Tell you what, let's run it on the same graph that we started BFS on. So again, here's the adjacency list representation. Let's see, 1 to 2 and 3, 2 to 1, 4, 5, 6, 3 to 1, 4, 4 to 2, 4, 5 to 2, 4, 6, and 6 to 2, 5. Did I do that correctly? 2, 4, 6, no. 4 goes to 2, 3, and 5. Now did I do it right? Okay, so that's the ADJ array. It's a little sloppy, isn't it? So, discover, finish, and parent. I'm not going to really worry about the colors in this run, but yeah, I should have a color field, and that's getting filled in too. But I won't trace that right now. Okay, so I never really said what order that loop is going to be executed, did I? And I never really said what order that loop is going to be executed, did I? You know what I mean by order. This is a for loop. Which vertex do I take as x first? Which vertex do I take as x second on the second iteration? So forth. Our convention is, just as it was in BFS, that these loops are executed in increasing numerical order by label. So maybe I should mention that. So that goes for both the main loop of DFS and this for loop inside visit that processes adjacency lists. And for that reason, I've listed these adjacency lists in ascending order. It's perfectly legitimate to pick some other order. But of course, the results you get are going to depend on that order. Okay. All right, so where do we start then? It's increasing vertices. So we color everything white and set all the parents to nil. And I didn't bother to initialize the discover and finish timestamps. So the initialization is done. We set time to 0. I'm just going to keep track of that in my head. You don't necessarily have to do that. And then we enter the main loop of DFS. For all x, take in increasing order by vertex label. That means I start with vertex 1. So therefore, this loop is 1, 2, 3, 4, 5, 6. Okay? So if color of 1 is white, and it is, 1 is undiscovered, what do? visit 1. So the first thing I visit is 1. That means color 1 gray. That's a discover event. So I discover 1 at time 1, incrementing time from 0 to 1, then putting that stamp on 1. And then now I process 1's adjacency list. If color 1, that's color of what, I'm sorry, the first thing on its adjacency list is 2. If color of y is white, that is, if 2 is undiscovered, set its, and it is, 2 is undiscovered, set its parent to be 1, and then visit 2. So I'm still, at one level higher in the recursion, I'm processing the adjacency list of 1, but now I'm already visiting 2. What do? We've got to go back to the beginning. Color 2 gray, set its discover time to be 1 more than 1, that's 2. Discover 2 at time 2. And then process 2's adjacency list. Okay? So the first thing on 2's adjacency list is 1. Has 1 been discovered? Yes, it is. It's been discovered in a call to visit that is one level higher in the recursion than we are right now. So, yes, that's been discovered. So we skip all this and just go to 4. Has 4 been discovered? No, it's not. So we set the parent of 4 to be where we're discovering it from. And that happens to be 2. No, hang on a second. Yeah, 2. And then I visit 4. You visit 4 by coloring it gray. Now I'm 3 levels deep in the recursion. Set its discover time to be 1 more than 2. And then process 4's adjacency list. So now I'm 3 levels deep in the recursion. This is kind of hard to follow, isn't it? You know what would be really helpful? If I had some kind of record of where I've got to return to. The way to do that is to be drawing this DFS forest at the same time. So 1 had as a child 2. 2 had as a child 4. All right, that's all that this says. 2 has parent 1, 4 has parent 2. Now I'm on 4's adjacency list. 2 has been discovered, so skip it. Next item on 4's adjacency list is 3. Has 3 been discovered? No, it's not. So I discover it, and so I set its parent, rather, to be where I'm discovering it from. That is 4. So the parent of 3 is 4. And then I visit 3. Now I'm 4 levels deep in the recursion. Visiting 3, I process, well, what do? I color it gray, set its discover time to be 1 more than 3, that's 4. Now process 3's adjacency list. But 1's been discovered and 4's been discovered by this time. So I finally get to the end of this loop in one of these calls to visit, and I'm in the middle of 4 calls to visit. I hope you notice. So I finally reach the end of this loop, and I can color a vertex black. That is 3. 3 gets colored black. And its finish time is ready to be set. Its finish time is 1 more than 4, that's 5. And I return from 3. Returning from my call to visit 3, but I forgot who I called, what was its parent? If you're drawing this forest at the same time, you don't have to question, or you can see exactly where you go back to. I got to visit 3 from within a call to visit 4. So I just finished 3 on the adjacency list of 4. Now we go to the next iteration of that for loop. This is 3 levels deep in the recursion. To visit 5. Visiting 5, has 5 been discovered? No, it has not. So I set the parent of 5 to be 4. And then I visit 5. Visiting 5, what do I do? Color it gray, set its timestamp to be 6. That's the time I discover 5. And then process 5's adjacency list. 2 has been discovered already, skip it. 4 has been discovered already, skip it. Has 6 been discovered? No, 6 has not been discovered. So what happens? 6 has its parent set to be where I'm discovering it from, namely 5. And then I visit 6. So what happens when I visit 6? First thing is I color it gray. The discover event occurs at time 7. And then I process 6 adjacency list. 6's adjacency list. But by this time, 2 has been discovered, 5 has been discovered. So I finish 6's adjacency list. I color 6 black, and then I set its finish time to be 8. That's 1 more than 7. And I return for my call to visit 6. This is only the second return that I've hit. Where do I return to? I return to 5. So I return to 5 from my call to visit 6. I'm at the end of 5's adjacency list. So now it's time to finish 5. Color it black, set its discover time to be 9, and return for my call to visit 5. Who do I return to? Visit 4. 5 was the last vertex on 4's adjacency list. This is really sloppy. I'll try to clean it up when I scan it. So I return to 4. Now I'm done with 4's adjacency list. Color it black, set its finish time to 10, and return from 4. To who? To 2. I return to 2. This is on 5's adjacent, or rather on 2's adjacency list. I just got back from visiting 5. What's next on 2's adjacency list? 6. But by this time, 6 has already been discovered, so I skip it. Finish 2 by coloring it black, set its finish time to 11, and then return to 1 from 2. Next thing on 1's adjacency list is 3, but that's already been discovered. So I finish 1 by coloring it black and set its finish time to 12. So this is the DFS forest. It consists of 1 tree. It's encoded by these parent fields. These are the discover and finish timestamps. That's what DFS does. Okay, so we'll discuss more of this next time, but I suggest that you run DFS on other examples. I'll do more examples on Monday. I will post PA5 also. Hang on. Those of you who have not turned in your homework, put it on this table. Those of you who have not picked up your homework, they're at the base and foot of the stage. Please leave the stage, get down there on the floor to pick those papers up. You're turning in alpha order, and you're picking up in alpha order. It's never been this organized. Be happy. It isn't.